Good morning, ladies and gentlemen. Welcome to this webinar on quantum simplicity, a tour of complexity science in a quantum world. This event today in the morning is jointly organized by the NTU Institute of Advanced Studies and the graduate student clubs of the School of Physical and Mathematical Sciences and the School of Computer Science and Engineering. I am Nondish from SCSC and I will be your host this morning. Before we begin the talk, let me take this moment to introduce our distinguished speaker, Professor Mila, who is an Nanian assistant professor in the School of Physical and Mathematical Sciences. He leads the Quantum and Complexity Sciences Initiative after being named a NRF Fellow in 2016. Before that, he was part of the faculty at the Institute of Interdisciplinary Information Sciences in the Tsinghua University under China's 1000 Talent Program, and he earned his PhD in the field of quantum computing from the University of Queensland in 2009. He is recipient of the 2009 SPMS Research Excellence and Teaching Excellence Awards, also winning the 2020 IBM Quantum Key to the Future contest. So let me take this opportunity to welcome Prof to this webinar. Before we start, before we start, here's a quick reminder to our audience that along the course of this presentation and the talk, if you have any questions, there's a section on your screen down below, which is called Q&A. Please type in your questions there so that once the talk is over, we will go through those questions one by one and then address them as many as possible as time permits, right? So please make use of that facility in the Zoom setup. And I think that should be fine. So over to you, Prof.
Great, thank you very much. So it's a pleasure to be here this morning. It'd be nicer to speak in person, but it's also nice to speak to meet all of you virtually as well. To give you a brief tour of some of my research, I think really highlights the integration between the information and the physical sciences, which kind of reflects two graduate schools that jointly organize this talk. So the title of this talk is really this idea of a tour of complexity in the presence of quantum observers. So what I want to basically talk to you guys about is some thematics in quantum information and some of these big ideas in complexity. And then we're going to see how they merge together. And for, let's see if this works now. Okay, great. So for those of you who don't know me, I'm sort of situated primarily at the SPMS at NTU, where I'm associated both with the Department of Physics and the Department of Mathematics. I'm also co-affiliated with the Complexity Institute also here at NTU, as well as the Center for Quantum Technologies at the National University of Singapore. So it's a bit of a mouthful, and it really captures the cross-disciplinary theme of a lot of my research. And so thematically, this talk will be the same. It'll be about the interface between sort of complexity and quantum mechanics. So let's begin with, let's start our story with a quick introduction to what the quantum world looks like, or well, what it doesn't look like. Our story then begins with these ideas of the double slit experiment. Now, many of you probably have seen this already in high school or junior college sometime, and you probably fell asleep during these talks. So hopefully I can introduce this in a slightly more exciting manner. Now, when you first saw the double slit experiment, it was likely explained in terms of waves. The idea is that we have this light source here, and there are two slits. And when the light source comes across and hits some sort of screen on the other end, and we look at the brightness and we look at sort of light hitting this fringe, we see bands of darkness followed by bands of light, sort of in this oscillating manner. And the classical explanation about this is to think about light as a wave. We say that when here in the center, the distance between this slit and this point and this slit and this point are the same. So we get this constructive interference. And as we go along the screen, we get sort of half wavelengths. So we get this destructive interference and so on and so forth. And everything sort of made sense. Until, of course, we start thinking about light not as just a wave. In 1904, Albert Einstein was one of the first to propose the photoelectric effect, which said that light fundamentally came in quanta. That is to say that once we weaken that light source sufficiently, there'll be only a single photon traveling between the source and the screen at any one point. And of course, once that happens, we can still repeat this experiment, and where we have an accurate photodetector here, and we just record where each photon hits. And sure enough, if we do that, what we gradually get is we collect statistics, and we end up seeing the same interference fringes. And this is pretty surprising, especially when we can repeat the same experiment with not just particles of light, but also things like electrons or atoms, or even in this case, a complex molecule of 60 carbon atoms. So in all these cases, what looked to be a particle was still able to interfere. Now, if we sort of step back a bit, this should look fundamentally strange, because it's kind of like imagining that we have a goal there, and we have this person kicking these soccer balls, kicking them one at a time. So there's at any time there's only one ball. It can't interfere with anything else, and yet somehow, remarkably, all the balls land in exactly the places where we expect sort of a constructive interference, if that ball was a wave. And for a long time, people struggled sort of to rationalize this, and when most of the rational explanations disappeared, I guess people had to turn to less rational ones. And the less rational explanation first proposed by Erwin Schrödinger was to have a wave equation for these particles, which is now known as the Schrödinger's equation. And the idea is to say that if a particle has nothing else to interfere with, but still has an interference pattern, then it must somehow interfere with itself. So this gave birth to these ideas of quantum mechanics, whereby a particle is able to somehow traverse both of these slits at the same time. And I'm here just going to label them 0 and 1 as a foreshadowing of information theory that we'll talk about later. And what happens is only in this way can we sort of explain that, okay, this particle is going through both slits simultaneously, and therefore it is somehow interfering with itself, and in doing so, we are able to see these interference patterns. But of course, when we look at this, the first thing to say is, no, wait, that can't be true. This is crazy talk. So why don't we put a detector here and just see which side that photon actually goes through? And sure enough, if we do that, every time we can register, okay, from the bottom pass, top pass, bottom pass, top pass, etc. And every time the photon behaves mysteriously exactly like a particle. So every time it goes through either one or the other slit, and the wave properties doesn't look like it's there anymore. And in particular, while we can detect the particle here, by the act of measurement, what ends up happening is we've disturbed the interference pattern. And at the screen, we no longer get that oscillating pattern of bright and dark fringes. And we instead get these two bright spots wherever these light sources are most likely to hit. So what went on there? It looked like nature was somehow able to tell that it has been measured. And this, of course, is deeply troubling to scientists at that time. Now, some of the explanations, of course, that surfaced was people still trying to be rational about it. They said, okay, maybe when we make a measurement, what happens is that we disturb this photon in some way, so we knock it, so it's either knocked to the top pass or to the bottom pass. And people try to rationalize these things using sort of these semi-classical explanations. And I want to demonstrate an interesting thought experiment that shows that how fundamentally different quantum mechanics actually is. And it's what's known as a quantum bomb detector. So imagine a scenario where you have a stockpile of bombs. So basically you're given this box, and in this box is a bunch of bombs that look externally completely identical. And your sergeant tells you, okay, what's actually going on here is that there are some good bumps here and some bad bumps. The good bumps are the ones that whenever you see a photo detector, whenever a single photon hits them, they explode. They're highly sensitive, light-activated bumps. The dud bumps don't interact with photons at all. And your goal is to take this box and distill the good bumps from the bad bumps. At least make sure there's a few that works. When we think about this, classical strategies don't seem to work very well. So we can, of course, take each bump, we can shine light, we can shine a photon at it, but then boom, we've just lost a good bump. And we go, oh, okay, that was a working bump, but too bad it's gone now. And so there's no way to directly extract a good bump and make sure that we can use it in the future. And this is where our interferometer can come in. So how do we make sure that a bump works without blowing it up? And the idea is to take what's called one of these single photon interferometers, and the way it works is very much in analogy to those two-slit experiments I outlined before. So what goes on here is we have some sort of light source, and it's going to hit this beam splitter. So half of the time, half of the light is going go on the top arm, half the light is going to go on the bottom arm. And if you work out sort of through the wave equation of motion, what happens is it's going to be destructive interference going up there and constructive interference going down here. So all of the light will travel down in this bottom arm. And that can be easily explained if light was a wave. But again, let's weaken that source. So we have a single photon emitter. So every time we only have a single photon. In this case, that single photon will, well, 50% of the time go up and 50% of the time go down. But nevertheless, what we find is that the same phenomenon as two-slit experiment happens. The photon somehow traverses both paths so that it can interfere with itself at its end to ensure that after this interference, the photon always travels down this bottom path and never the top path. So in particular, if we were to put a bump, if we were to put a photo detector here, we would see nothing. So now let's see how that helps us with the bump detection. Imagine that we placed a bump in the bottom arm of this interferometer, and suppose this bump was a dud. Well, what's going to happen is that that photon and the bump is not going to interact with each other at all, and so the interference pattern is not disturbed, and the photon is guaranteed to travel through this bottom path. So if we had a detector here, we would see absolutely nothing. Now imagine now if the bump works. Well, half of the time, of course, the bump's going to see that photon. It's going to detect that photon and see it, whereby, well, it doesn't really matter what happens anymore because we have lost the bump. But the other half of the time, the bump is on the bottom path. It's looking for the photon. It doesn't see the photon. But nevertheless, the act of measurement disturbs that interference pattern so that at this point, the photon no longer travels on the bottom path at all, and it's collapsed to just traveling on the top path, whereby it can no longer interfere with itself here. So it's just like it hit the interferometer, the beam splitter the first time, and it's 50% of the time the photon will shoot up, and 50% of the time the photon will shoot down. So if we were to put a photo detector here, and we were able to see a photon, then we're guaranteed that this bump here works, even if it has not blown up. Of course, this doesn't happen all of the time. We'll lose half of the bumps when the bump detects the photon down this lower path, and half of the time the photon will still fly down this way, so we get an inconclusive result. But a quarter of the time, with a working bump, we will know for sure that it works without sort of blowing that bump up in the process. And of course, if we get an inconclusive result, we can always feed it back. And so we can actually improve our rate of success up to 33%. And indeed, this experiment was sort of experimentally verified in 1995 as one of the first sort of key experiments that verifies how strange quantum reality is. And the key thing here is that if we think back about it, it is very strange because what's going on here is that we can drag these two these two mirrors here arbitrarily far apart. So this one's situated on Earth, and maybe this one is situated on Mars. So that this bump here could be arbitrarily far apart from where the beam is. And nevertheless, somehow, the information contained in this photon can tell us something about this bomb. So information is somehow information is sort of being affected in a non-local manner. And this is what makes quantum mechanics fundamentally strange. In particular, if we assume that reality was real and we assume that this photon always had a definitive path, then we would conclude that, okay, we saw the photon here, so the photon must have traveled down here, up here, down along here, and up here, whereby I would say, if the photon went across here and was on Earth, and this bomb was situated somewhere on the Mars, how is it in the world possible for this bomb to have any effect on this photon? And for these reasons, quantum mechanics is a very strange type of reality. And it happens to be the reality we live in. And it's nicely summarized by Niels Bohr here, who said that, okay, everything we call real is made out of things that cannot be regarded as real. If quantum mechanics hasn't profoundly shocked you yet, you haven't really understood it. And what he was getting at is that for quite a while in the 1920s, physicists were busy computing sort of the spectra of atoms quite happily with the rules of quantum mechanics. And so they thought they understood it. But when you think deeply enough and think about one of these thought experiments, very strange things happen. And you're like, where is the information going? And this is just really strange. So now let's see what that means in terms of information processing. So let's look at the anatomy of a quantum bit. And to do that, let's first look at the anatomy of a classical bit. So most of us are familiar with classical bits. Of course, you learn a lot about it if you were doing computer science, and otherwise you'll be downloading movies and so on, so you probably still know about bit rates. And so a bit is a fundamental representation of data, and it's really just the answer to a yes or no question. And if we think about how any bit is stored, it has to be stored in some physical medium, which means that that physical medium has at least two distinguishable states. One state which we call 0, and the other state that we call 1. And we can sort of represent them in this pictorially as the top point and the bottom point of this spherical shape. Now, somewhere in the middle here is our state of complete uncertainty. That is basically when we have, say, a coin or a random coin, and we didn't look at its result. We have no idea whether the bit is 0 or 1. And that's what, if you're doing information theory, people would say maximum entropy. And that's really just a classical probability distribution where the coin, where your bit is either 0 is 0.5 or 1 is probably 0.5. And the entirety of classical probability theory or classical information processing is really constrained to this vertical line. It's basically about either we have a 0 or 1 or some probabilistic mixture of zeros or ones. We're just not certain with it 0 and 1, and with some weighting P0 and P1. You can think about these as biased coins. This represents a state of complete uncertainty, and as we get to the edges, we end up with states of certainty. Now, these states can, of course, be represented in a quantum system as well. We can imagine that we put a photo detector here, whereby we can say that z equals 0, meaning the photon goes on the upper pass, is 0, and 1, meaning the photon goes on the bottom pass, we will think about that as a 1. And by adjusting the initial location of our light source, we can encode one piece of information. And then someone else can, of course, measure this photon and read out that piece of information. The interesting thing, though, with a quantum system is that there are other ways of storing this one bit of data. For example, if we went back to our interferometer, we could have put in that beam splitter here, and then what we would have had is we would have had this photon going through a superposition of both up and down. And so in the quantum information language, we write that as the 0 plus 1. Don't worry about this coefficient here. It's really just as to create normalized vectors purely for mathematical reasons. In this talk, you don't need to worry about that at all. Just think about this as an equal superposition of being on the top and the bottom. But the key thing that makes it very interesting is that there are many ways of being 0 and 1 at the same time. In particular, if we put the laser source down here, at this point in time, we still have a superposition of being 0 and 1. But we can tell these two states apart perfectly because if we were to hit this with a second beam splitter at this point, then in this case, in this scenario, our photodetector would definitely be dark, whereas in this scenario, our photodetector would definitely detect the photon. So we're still able to send one piece of information. We're able to sort of encode one piece of data here, even though looking at it classically, we just have both of them being half up, half down. But the key thing in quantum mechanics is it's not just about being able to be simultaneously 0 and 1, but about having many ways of being simultaneously 0 and 1. We can have 0 plus 1, or in this case, mathematically, people can represent this as 0 minus 1. And 0 plus 1 and 0 minus 1, people call them the plus state and minus state, are equally valid ways of storing a bit because we are able to distinguish them. And we can call this the variable x equals 0 and the x equals 1. And notice that I'm just looking at the information storage here. So at all cases, we really only have two of these configurations. Classically speaking, we just have up and down. But somehow we're fitting all these other configurations in between. And that can be represented visually in a quantum information processor by having a plus state here and a minus state here in these 2 points of this circle. And sure enough, the beam splitter is a logical operation that allows us to transform from 0 to plus and 1 to minus. And for this reason, it's given the nickname the square root of the NOT gate. Because the NOT gate goes the whole way through at flip splits, but the square root of the NOT kind of goes halfway. And we can flip forwards, and of course, we can also flip backwards. And in fact, every single point on the surface of the circle is a valid quantum state. And we can prepare them by simply adjusting this beam splitter. So instead of being a 50-50 beam splitter, we can change its reflectivity so that the photon is more likely to go up and down. And then we're able to explore this entire region of this entire surface of the circle. So the entire surface of this XZ plane. And so in this case, what we see is that quantum information or quantum bit has much richer behavior. It can have many different ways of storing a single classical bit. It can store the classical bit in terms of these X values, which stores what happens if I interfere these paths, or it can store them in the Z values, which is what happens when I simply measure these paths. And they're both equally valid ways of storing a bit. And but of course, one of the key consequences, though, is that a quantum bit nevertheless is still a bit, because while there are many different ways of storing the bit, if we were to measure in the Z direction, we would destroy the interference pattern here, and we have no idea what the X encoding is anymore. Whereas if we measure the X encoding here, that relied on us never looking at the Z encoding in the first place. And so we have the uncertainty principle on a single bit of information. There are many ways which we can encode one bit of data, but we can only choose to extract a single bit of data. And this is an information theoretic way of capturing the uncertainty principle. For those of you who did some communication theory, it can be expressed in this form as an information theoretical uncertainty principle, saying that our uncertainty about the X variable and the Z variable, when added together, must be greater than 1. So we're either uncertain about one thing or we're uncertain about the other thing. Now, where things get really weird is now when we take these bits and we have many of them joined together. So suppose we have two quantum bits here, one state of this form and a state of this form. And this is an operation called control knot that allows us to build what's called an entangled state, which is to say that we are able to build a state that's kind of like this. Mathematically is represented this way. What it means is that either the two qubits are both pointing upwards, or the two qubits are both pointing downwards. But we have a superposition of these two things happening at the same time. And this state is very weird because actually when people create a state, and if you do some elementary quantum mechanics, one can show that there's a superposition of zero pointing up, both pointing up and both pointing down, is actually exactly the same state as superposition of both spins pointing left and both spins pointing right. So what that means is that if we were to measure the first qubit, say in the Z direction, or measure with a 0, 1, then the second qubit is guaranteed to be also in the z direction. Similarly, if we were to measure that first qubit in the x direction, the second qubit would also be guaranteed to be the same in the x direction. So the two qubits are perfectly correlated in both the x variable and the z variable. But each individual qubit, by the uncertainty principle, can only sort of know, we can only find out about individually only either its x or its z. So somehow a quantum system can know more about another quantum system than what we can find out about information contained in itself. That's the power of quantum correlations. You can store more data in the correlations than in the bits themselves. And this has no classical counterpart. With classical bits, whenever we have one bit of data, at most we can store one bit of information about something else. But a quantum bit can somehow, while you can only retrieve one bit of data about itself, can store up to two bits of data about something else. And that's where the power of entanglement comes from. Of course, so far, everything sounds very theoretical and abstract. And one might ask, okay, where are we getting at? I mean, these things, these quantum mechanics, quantum information is kind of interesting, but we can't interfere cats. So what is a big deal? And for a long time, all of these things were considered mathematical curiosities. And it was only fairly recently that people started thinking, wait a minute, quantum mechanics being so complicated isn't necessarily a bad thing. Maybe it can help us solve complicated problems. And the key thing comes from this entanglement. Because of the fact that these correlations can contain so much more information, when we have two qubits we see, what we can have is a superposition of all the possible orientations of spins. So we start off with two parameters here, and once we end up with two quantum bits, we get four parameters here. And once we end up with three quantum bits, we end up with 8 parameters. And the very interesting thing here is that if you took one of these parameters, say the first qubit, and you decide to flip it from a 0 to a 1, it would affect half of these parameters. So with a single action, you can affect an exponential number of different parameters. So if we were able to encode classical information in this form, we can encode an exponential amount of data in a linear number of quantum bits. And we can affect an exponential amount of data by perturbing a single quantum bit. And that is really where the power of quantum computation comes from. And since, I should mention that, and this, of course, scales very impressively because it is exponential. As anyone who have tried to solve exponential time problems would tell you that once you solve a traveling salesman problem with more than 300 cities, it gets crazy. And similarly, once you have more than 300 qubits, the number of parameters required to specify them goes crazy too. It's more than the number of atoms in the universe. So once we are able to, say, process 300 qubits coherently, there's no way we can simulate that using a classical computer, leading to these ideas of quantum supremacy, that once we get to a certain threshold, there's no way for a classical computer to be able to replicate what a quantum computer can do. So, since the 1980s, this has basically, quantum information processing has turned from this curiosity to something of real practical interest. What's often coined as a second quantum revolution. There is, of course, quantum computation, as I mentioned before, but a lot of other things, these quantum properties, turned out very favorable as well. Quantum entanglement is very fragile, and at first people thought it was always a bad thing. But when you want enhanced sensitivities, being fragile is actually a good thing. And so it turns out that very fragile quantum states make excellent quantum probes, and we can thus build a new generation of sensors. And this has sort of currently escalated into this US-China Cold War in quantum sensing technology versus stealth technology. The third thing here is cryptography, which of course again comes from the disturbance because of the fact that when we measure a quantum state, we're guaranteed to disturb it. It allows us to encode information in a way that we always know if someone else tampered with it. So we can know if someone was eavesdropping, leading to sort of information security known as quantum cryptography. But what I want to emphasize today in this talk is something that is closer to the ideas of complexity science, which is the idea of looking at quantum modeling and simulation. And at first, this seems to be pretty surprising because when we think about complex systems, we think about very large macroscopic systems, maybe interactions between cities or sort of the rise and fall of stock markets. So they don't seem to have any relation to atoms and photons at all. But because they both can be expressed in the language of information, we can draw a lot of interesting connections. So the way that this works is as follows. Imagine that we have a complex system out there, so that we record a bunch of data from. So we get a big string of data, and we want to build a model of this data. This is a very common problem in in complex modeling, and one of the things that people often want to optimize in these areas is to say, okay, what is the least amount of information I need to store about the past to still get an accurate prediction about the future? And the motivation is twofold. Storing and collecting data costs resources. So ideally, we want to store as little resources as possible, just because it takes energy to do so. But also from more fundamental perspective, the more that we can isolate the data that's relevant, it also represents better understanding. Because when we don't understand anything, we kind of have to store everything because we have no idea, say, what causes the weather tomorrow. So we we just check our horoscopes and whatever else. But as we get better and better at building scientific models, we start knowing what are the causes of the future, and you can sort of disregard irrelevant information. And in doing so, we get both a more efficient model and also a better understanding of what in the past is actually an indicator of future behavior. And that indeed is a lot of the motivation behind these dimensional reduction protocols in data science. And it also really reflects one of the key things that really gave birth to physics, which was Isaac Newton's statement that when we're trying to build models, we should ignore normal causes, then both true and sufficient to explain the appearances. So this idea of Occam's razor, try to explain things as simply as possible. And so in complexity science, people have sort of formally formulated this problem. And in the simplest incarnation of a time series data, is basically this idea of, okay, we have this sequential data coming through here. This is all the stuff that happened in the past. This is all the stuff that can happen in the future. And suppose it's governed by some probability distribution that correlates past and future. What's a model that generates that? So what is a model that can sort of take information from the past, store it inside our memory in the present, so that systematic simulation at future time steps allows us to sequentially generate the right statistical simulation of the future. And so you can think about these as basically hidden Markov models, what they call it in the technical terms, of a stochastic sequence. The physical way of thinking about this is that we have some system here. Every time step we're feeding a blank tape. It does the same iteration at every time step, and then outputs the correct output at that time step and updates its memory, goes forward in the next time step, and so on. And everything can then be described by these transitions between some sort of finite state machine. Now, the idea then is that the information we have to store about the past to be able to generate the future is exactly this cutoff here. It's information that has to propagate from one time step to the next time step. And we want to minimize that. And so the minimal, which is quantified in terms of Shannon entropy, if you're not familiar with that, don't worry. Just think about that as the number of bits that's required to sort of store the information here so that we can generate the right simulation. So the minimum amount of information needed to do that was given a special name by Jim Crutchfield, one of the leading complexity scientists who's currently in the Santa Fe Institute. He sort of gave these things the name statistical complexity, and he said that, look, I think of statistical complexity as an intrinsic measure of how complex a process is, but it tells us the minimal resources we need to be able to simulate it in this causal manner from sort of past to future. And since he first came up with this idea, and there has been systematic ways of finding the simplest machines of trying to bound the statistical complexity, and it's been applied to a diverse range of different phenomena from sort of analysis of financial data to atmospheric networks and so on. And what we were interested in was, well, everything so far was done classically. We assumed that that model going across stored classical information. What happens if that model was quantum mechanical? What if it stored quantum data? And one of the first things that we demonstrated was that classically, it turns out that in a lot of scenarios, even the optimal classical models still waste some information. We're still storing data that is actually not correlated with the future. And whenever that happens, we can build a quantum model that does better. Now, the formal proof is a bit beyond the scope of this talk, but we can illustrate these ideas with a simple example. So here is an example which I call the perturbed coin. You imagine that there's a box with a coin inside. And what happens is that every time step, what we're going to do, we're going to take this box and we're going to shake it. Not too hard, because if we shake it too hard, we just get a completely random process. The coin would be just completely unbiased. We shake it just a little so that there's some probability Q that it flips between heads and tails, but this Q is generally significantly less than 0.5. So we get some correlations between each output in sort of consecutive time steps. In particular, you can think about the output as a stochastic sequence, which when you do data analysis on it, what you find is that the frequency of, say, L consecutive ones would occur with proportional to 1 minus Q to the power of L. So once we have this data sequence, the question is, okay, what's the simplest model to be able to sort of simulate it, to be able to sort of generate the right predictions? And if we think about it fairly carefully, well, what happens is that this process is Markovian, because it just depends on the state of the last coin. So really, the only thing we need to store is about whether the last output was 0 or 1. However, at the same time, we can't get rid of this information because the future does depend on whether that past was 0 or 1. So using any classical model, it turns out we need to store one bit of data, namely the state of that coin. But this is a bit weird, since if we think about it, once this imagine that we shake this box harder and harder so that that P goes progressively more and more towards 0.5. What happens in that scenario is that the future and the past becomes progressively less and less correlated, because this data string is going to look progressively more and more random. So past contains progressively less and less information about the future. Yet we still need one bit of information. So what's going on? Well, the key thing here is that the classical model is wasteful, because once we're storing the state of this coin at this present time step, but even if we see the entire future, and then we say, wait, at time step t equals 0, where did I come from? I still don't know for sure whether that came from heads or from tails. So some of that information isn't being propagated in the future. So what can we do? Well, can quantum mechanics give an alternative solution? It turns out it can, because classically, we have a binary choice. We can either write down a piece of data or not write down a piece of data. Quantum mechanically, just like the Schrodinger's cat or the photon superposition up and down, we can choose to do a superposition of writing down a piece of data and not writing down a piece of data. Sounds a bit weird, but it seems to work. And what that means in practice is that when we have one of these quantum bits, instead of storing the relevant information about whether the coins in heads and tails, instead of in these points on the circle, we store them in these points on the circle instead. And when we do that, what happens is that while we're sacrificing some distinguishability in the z direction, because now these two states are not perfect, they don't give us perfect z statistics, we're building up a bias in the x direction, and that means that our quantum bit still has some extra information extra capacity to store more data if we were just to do flips along the z-axis here. So we're only using part of that quantum bit, and this can be formalized from the notion of what's called quantum entropy or volume entropy. And what it turns out is that the information that's needed is strictly less than their classical counterparts. And we can still nevertheless build up a quantum circuit where we feed in the state and then we feed in blank tapes that generates the right statistics. Now, the interesting thing about this quantum circuit is that it works quite differently from the classical ones. The classical ones, what happens is that once we get the output, the classical machine goes, oh, did I output a head or tails, and I will update that on my memory. the model, the quantum simulator does something very different. It throws this as output and then doesn't care about it. But the output is entangled with the memory. So whenever a third-party observer looks at that output, they automatically collapses the memory to the right state for future simulation. And so the quantum simulator saves the effort of looking at the last time step and therefore saves memory. And indeed, we were able to demonstrate this by experiment. This was our first proof of principle experiment back down in 2018, where we kind of encoded the quantum memory in the polarization of a photon. And in doing so, we were able to demonstrate sort of this memory advantage between sort of the optimal classical model, which hovers on 1, and the quantum model, which, depending on the probability of perturbation, can have drastic savings. Of course, at this stage, when we say drastic savings, we're still looking at sort of 1 bit of information. So things are not that impressive. But what we were able to do was we showed that we could generically build these circuits for very general non-Markovian processes. So where that sequence of, where that dependence wasn't just, when we look at the future, it wasn't just dependent on the very last emission, but it could be dependent on the last 100 or the last 1,000 emissions. And that's where things get really complex. And in these scenarios, what we end up is we can get scaling advantages. So what we can find is that we can get families of stochastic processes where classically the memory required to simulate them continues to grow, but quantum mechanically it can be bounded by some constant. And this memory can be directly translated to sort of comparing the number of classical bits versus the number of quantum bits. And in one of our very recent experiments done in October 2019, we were able to show this dimensional compression. So we were able to sort of take a stochastic process and sort of compress it losslessly. So in normal data science, people do a dimensional reduction, but usually there's small loss. Here, it was completely lossless, and we were able to sort of compress something that's normally 3-dimensional into a 2-dimensional system. Of course, in principle, we can do more, but practical quantum technologies presently is still fairly limited. So that sort of illustrates these ideas that, well, fundamentally, what is complex can really depend on what sort of information we use. And this is really, I guess, just the fundamental building blocks to a very exciting paradigm with a lot of interesting possibilities. I want to take the last 10-15 minutes of this talk to just go through 3 of those interesting things that we're exploring at present. The first is this idea about prediction and retrodiction. Now, when people studied the information cost of prediction, one of the very interesting things that they found was that the cost of prediction and the cost of retrodiction was in general not the same. If we had a sufficiently complex process, on one side it might cost more resources to do than the other. And this is a phenomenon that the complexity scientists called causal asymmetry. The intuitive way of explaining it is to show you this movie of a guy kicking down a door in reverse time. Now, the first time you probably see this movie, you're like, okay, what is actually going on? And then once you finally see the door, okay, it's a door that's been kicked down in reverse time. So it illustrates that sometimes when we reverse things get a bit more confusing. And perhaps a better illustration would be to watch any Chris Nolan movie, like, say, The Resident Tenant, where things are all happening in reverse and we have no idea what's going on until we watch the entire movie. So the basic idea is that in certain cases, when we see things in reverse and we try to do retrodictions, things are trickier, at least classically speaking. And one of the things we were interested in exploring is what happens when we build quantum models of retrodiction. And what we find is that that in many instances, this asymmetry can be wiped out completely. In particular, even if sort of retrodiction costs a lot more resources than prediction, our quantum models are guaranteed to use less resources than sort of, even if we don't quantum retrodiction, it's guaranteed to use less resources than classical prediction. And this sort of garnered this highlight in New Scientist about well, we might only see time because we can't think in quantum physics. They interviewed me, but they misquoted me a lot. So if you read that, they kept wanting to relate to the movie Ant-Man at that time. And I said, and so yeah, there's quite a few quotes about Ant-Man. Don't take it too seriously, but it does have some interesting stuff about that if you want to listen to it. The second thing area that we're looking at is in terms of generating a superposition of possible futures. So far we talked about simulation, which is when we took each one of these outputs and we measured it, and we generate right stochastic sample. But quantum mechanics, these quantum models, give us a different degree of freedom, which is that if we leave everything unmeasured, it remains entangled in the memory. And what happens is that this memory sequentially prepares a large entangled chain of quantum bits. And that entangled chain of quantum bits is essentially stores a superposition of all possible conditional futures of a stochastic process. In effect, it prepares what the quantum algorithmic software people would say a quantum RAM for the conditional future of a stochastic process. And this is exactly the thing that it prepares as a superposition of all possible future outcomes weighted by their likelihood of occurrence. So if we were to measure them in the standard basis, we will be able to generate the right stochastic sample. But if we don't, we might be able to do something more interesting. And this, if you're scared of this equation, just think of Dr. Strange. They're trying to sort of predict all 137,000 possible futures at the same time to look for that one future in which they can win. And here, once we have the superposition of futures, we can start thinking of running things like robust search algorithms so that we can search this quantum database for that one possibility that we're interested in. Or alternatively, in one of the experiments that we were recently able to do, is that we were able to build two slightly differing models, which generate two slightly different futures, and we were able to measure their divergence by computing the inner product between these two vectors directly. And this is something that would otherwise take an exponential amount of time because we're talking about an exponential number of possibilities here. But here, what we're able to do is we're able to sort of compare only a linear number of qubits using a quantum interference of two different futures. And the way this can be done in practice is we encode the futures into the path degree of freedom of two photons by having them go through these loops. This is like the first output, the second output, the third output, and the photons position in the photon's position then encodes as actual output. And then we're able to take those two photons and interfere them. And the interference pattern gives us exactly the inner product. And in doing this, we were able to build up a quick way of understanding how quickly two models diverge in their future predictions. And this could potentially have applications in sort of machine learning, where we're interested in training models so that they more quickly align with the statistics that we want them to align with. The final thing that that I want to quickly outline is that so far I talked about sort of modeling standard passive process. So one means a stochastic sequence. We observe it, but we can't change it. In general, though, when we think about more general things like stock markets, well, we can affect them. We are able to sort of choose to give them an input and then receive an output. Or in terms of agent-based modeling, our agents in computer science, at every time step, they are receiving a stimuli from the environment, and then they're using that to decide on an action. And the question is, can we simplify these adaptive processes as well? And here I want to illustrate this by a very simple example. Imagine that we have an extremely simple Turing test, a very simple Turing test. This is from a movie taken from Blade Runner here. And so the idea is that agent is asked one of two possible questions. The first question is, do you like electric sheep? The second question is, are you human? And the only behavior required the agent to do to pass this test is that if he was asked the same question twice in succession, he has to agree with, his answers must agree. But if he was asked a different question, then his answer to the second question must be random. Now, if we think carefully about how we can build a machine that does this classically, we need to keep track of two pieces of information. One is what question was asked before, and the second was which answer did we give. So we need two bits of information. And you can build up a finite state machine that sort of replicates this in this form. So this is asking the first question, this is asking the second question, and these are the four states. So if we ask the same question twice, we keep giving the same answer. But if we ask a different question, we randomly, so if we're in this state, we ask a gray question, we randomly sort of output one of two outputs and transition to one of two different states. And that works perfectly fine, requires 2 bits of data. But if we think carefully, what these four states can correspond to in a quantum bit are basically our qubits pointing up, down, left, and right. And the reason we can do that is because of the uncertainty principle, which says that after we know the z position of a quantum bit with certainty, we lose all information about its x position. But if we were to measure the same direction twice, we always get the same answer that agrees. So we can get the exact same behavior with a single quantum bit by choosing at each time step to either, when we are asked one question, we measure that bit in the z direction. In the other case, we measure it in x direction. Of course, this is a reverse engineered problem. The reason why I gave this question is because it had a very simple quantum solution. But in actuality, we can prove a systematic result to say that for most interactive behavior, a quantum processor, what's called a quantum transducer or quantum agent, can use less memory. And as always, you have this memory here, we have a probe, and depending on what question we ask, we choose a different measurement. We're asking the quantum system by choosing to measure it in different bases, and it will give the right answer. So here, the choice of measurement basis is like the input stimuli, and the output is like the output action. And one of the immediate consequences, even when we can't build these agents directly, is the benchmarking of quantum processes. This is a bit advanced, and in the interest of time, I will skip it. But as a quick summary, the take-home messages here is that quantum mechanics is really fundamentally a very different beast. It's not just classical computers running faster. So it is fundamentally because quantum pieces of data are not realistic, that a qubit does not have a well-defined x and z state until you measure it. And because of that, we can harness it to do some very remarkable things. The second case is the take-home message is this idea of simplicity, which is that because quantum systems, with their peculiar properties like entanglement and non-local realism, they are very complex systems. But ironically, because they're complex, if we are able to harness that complex information processing, we can make other things look relatively simpler. And the third thing is that so far, this interface between these fields are really just at the beginning. We've got these superpositional futures, but we're still finding new ways to use them, say in quantitative finance. We've got this idea that quantum agents are faster, but we don't know how much faster they are, and we haven't yet applied them in a reinforcement learning algorithm. And those are all very interesting possibilities. And indeed, one of the other things that I haven't touched upon, that's a big third centerpiece of our research, is the thermodynamics of these things. Because when we start thinking about agents, actually they're tied to a very interesting concept in thermal physics known as Maxwell's demon, which is that the ability to extract more energy from a system if you knew more information about what that system is. And so data processing, energy extraction, and quantum science are all very deeply intertwined. And these are really some of the themes, big questions that we're currently asking quantum advantages in learning and agency. We're asking what are the thermodynamic laws of learning? And we're asking, okay, can quantum processes be more efficient? The group that we have here, I don't know what happened to students there, some sort of text corruption. But anyway, currently our research group, we have a fairly large group here with 11 research fellows, 7 PhD students. This is the last photo before COVID hit. Now no one can have group dinners anymore. But we still do have potential opportunities through the Nanyang Presidential Scholarship, which I believe is due on the 30th of November. So if you're interested in these, I should say that usually most of my interest comes from physics students, but actually we want a good mix of data science, math, and computer science majors as well. Because really this is a highly cross-disciplinary field. And the group that we have is really got a mix of people in all these different areas of expertise. So if you're interested, do let me know and we can explore potential opportunities. And here are some references if you're interested in reading up a bit more about the stuff I talked about. Thank you very much.
Thank you, Professor. That was a wonderful talk. It's highly insightful and quite an eye opener, really, for me because
Thanks.
I have not particularly looked into this topic since I come from a data science background and work
Mm-hmm.
mostly in machine learning, but that's very much from a classical algorithms perspective. So
Absolutely.
yeah, so it's quite an eye opener for me at least. Uh, Now, the thing is, we have a few questions that have come from the
Mm-hmm.
audience. So I'd like
Sure.
to run through them, and you can just take some time to address. The first question
Sure.
is that the first question is more of a clarification, really. So it says, could you explain how quantum entanglement leads to computational speed up in the quantum computing framework?
Great. That's a very good question. I did go through this very quickly. So there are two key things that lead to the potential speed up. The first thing is the ability to store exponential amount of data in a linearly sized system. So when we look at the state space of a complex of us of a quantum system, so let me see if I can go back to that slide. It's a little bit here. Okay, great. So when we look at the state space of a quantum system, what we see is that when we have, say, 3 qubits, the state space is defined by a complex vector of 8 dimensions. So it's an 8-dimensional vector. Complex, don't have to worry too much about it. It's an 8-dimensional vector. Now, if we were to go to 4 qubits, it will turn out to be a 16-dimensional vector. And in general, when we have n qubits, we have a 2 to the n dimensional vector. What this means is that if we look at the amount of data a quantum computer can sort of at the state space of a quantum computer can capture, it grows exponentially with the number of qubits. And so this allows us in principle to take a very large exponential amount of possibilities and store it in a linearly sized quantum system. And we saw that when we did this future prediction, because when we had this conditional future over all these stochastic processes, then every time step our output, could be 0 or 1 if we're talking about a binary process. So every time the output could be 0 or 1. So if you look at the probabilities over a big string, well, there are 2 to the n different outcomes, and they all have their own probabilities. So if you were to store that probability vector, it's an exponentially large vector. So imagine just, for example, just storing that in a classical computer would take both an exponential amount of memory and certainly also an exponential amount of time. Now, what happened here when we did this, when we sort of stored that piece of data in a quantum computer, is that we were able to sort of use all of these coefficients. So each coefficient was like the probability of getting a 0, 0, 0, and the probability of getting a 0, 0, 1. But in general, in total, the number of quantum bits we used is linear, or it scales logarithmically with the dimension of the vector we wish to store. And because of that, we are able to sort of drastically save on memory costs. The second thing that gives the potential for quantum advantage is that when we manipulate a single quantum bit, say if we had this vector here, and say if we did a single action that flipped a single bit, so flipped the third quantum bit from a 0 to a 1, then what we can see is that that single action would have interchanged A and B, it would have interchanged C and D, it would have interchanged E and F, and it would have interchanged G and H. Because if we flip 0 and 1 and we get a new vector, well, these two coefficients interchange, these interchange, and so on. So what that means is that by single action on a single bit or a single gate has effectively interchanged an exponential amount of classical information. So we're able to affect an exponential amount of classical data with a single quantum gate. So these two things are what gives the potential for quantum computers to give advantage. Of course, I have to caveat this because If things were so simple, we would have quantum algorithms everywhere. Uh, Despite the fact that a quantum computer can store, well, the state space scales exponentially. When we read it out, due to the uncertainty principle, we can only actually read out a linear amount of data. We can only choose one basis to measure each of these spins and measure it. And so quantum computing is very much about manipulating exponentially large vectors and then trying to find a way to select a linear subset of that exponentially sized vector that contains information we actually care about. And if you look at, say, Thesseloyd's matrix inversion equation, they're all in this form. They start off with a large, exponentially large vector, then they invert that vector to get another exponentially large vector, and then they read out some information they care about, but they can't read out the entire vector. So we have to be very careful in building quantum algorithms. Cool.
Thank you, Professor. We have another question, which is sort of a continuation along the same line, which is if changing one part of the information changes other parts, does it mean that the information is dependent on one another? How can we say that in that particular case we are storing more information?
That is a very good question as well. Indeed, that argument works completely in the classical instance. In the classical scenarios, it is true that once things are correlated, as you know, the information, of course, they're less dependent, so you have less information in total. In general, you still have the same amount of information, regardless of whether you store it in the correlations or individually. Quantum mechanics is a little different in that the correlations has vastly more degrees of freedom than the local parameters. So one way of thinking about this is from a parameter counting perspective. If we think about a single qubit, what happens is that it actually has two complex. So these two, alpha A and B, in general are complex numbers, but because of normalization, you wipe out 1 degree of freedom. So a single qubit has 3 degrees of freedom. Now, if you look at 2 qubits, what happens is that you have each A, B, C, D are complex numbers. So you have 8 degrees of freedom, but then, of course, you wipe away 1 degree due to normalization, so you have 7 degrees of freedom. So 2 qubits here, we have 7 degrees of freedom. 1 qubit, we have 3 degrees of freedom. 2 qubits should technically have 6 degrees of freedom. Somehow, when we have 2 qubits with entanglement, we end up with 7 degrees of freedom. Each degree of freedom, of course, gives you an entire dimension to store more information. So I mean, the volume of information in the store is unboundedly more. But then if we go, but this, of course, gets even crazier once we get to, say, 3 qubits. In 3 qubits, the number of degrees of freedom for 3 quantum bits, if we think about it here, is 8 complex numbers, double, so that's 16 parameters, subtract 1, 15 degrees of freedom. But but if you think about 3 quantum bits individually, each one has 3 degrees of freedom. So we should only get 9 degrees of freedom if we thought about each quantum bit individually. Now, when we have classical parameter space, it doesn't really scale like this. So what happens is that quantum, the key thing here is with quantum systems, we get this exponential scaling in parameter space, which is more than what happens if we were just to think about these qubits individually. And so the question is very good. It's absolutely right. When these qubits are entangled, they are no longer dependent on each other. They're no longer independent of each other. But the space in which we can store entangled states is so great that we still end up storing much more information.
Thank you. The next question is, as much as more information can be stored in a quantum system than a classical one, in order for us to use the information, we need to make a measurement and destroy the state that was stored. Wouldn't that limit the amount of useful information we can actually access?
That is an excellent question, and that is exactly what I was saying about why it is very hard to design quantum algorithms. It is absolutely true that there is this theorem in quantum information known as High-level theorem, which says that you can only at most reliably extract one bit of information from each quantum bit. So the amount of information we can get out of a quantum system because of the measurement and the subsequent measurement collapse is bounded by the number of quantum bits we have. So while we are manipulating an exponential amount of data, the final data we can get out only scales linearly with the size of the quantum system. Nevertheless, though, that doesn't prohibit us from all potential quantum advantages. So one of the first quantum protocols that kind of that sort of illustrated this advantage is what was known as the Deutsch-Jozsa algorithm. And in this case, it is about you have this function and you want to know for sure, and someone tells you either this binary function, either it's constant, which means that it always gives the same output, or it is balanced, which means for half of the inputs it gives 1, and half of the inputs it gives 0. And so you can think about this, the amount of information you want to get out of this is just 1 bit, because you just want to know whether this function is balanced or whether it is constant. So you only want to read out this 1 bit of data. But classically, to try to read out that bit of data with certainty is very hard, because you imagine that you have this function and you want to know, okay, does it always give all ones, or does it give half ones and half zeros? So you try the first input, you try the second input, and okay, you get 1, you're like, I'm still not sure, I have to try the third input. And you can only be sure after you tried half of all the inputs, because then you go, okay, so I've tried half the inputs, the next input I try, I still get a 1. Okay, for sure, this is going to be a constant function and written a balanced function. But what happens is that quantum mechanically, because all we care about is this 1 bit of information, we're able to get exponential speed up. Since to work this out, we did have to look at an exponential number of possibilities, but we only cared about one piece of data about that exponential amount of possibilities. So if you look at all quantum algorithms, they all play this trick. With the linear equations, they're inverting a linear equation that is exponentially large, and they get an output that is a vector that's exponentially large, but they can't find, but there's no way for them to read out all the elements of that vector. But they can read out a linear number of bits about that vector. So if you're asking certain questions about that vector, for example, how well that vector overlaps with a different vector, like computing the inner product, then you get an efficient way of doing that computation, because you need far less information to get, you want to extract out far less information.
Thank you, Prof. The next question is, this probably comes from a student of yours who's taken a course,
Yes.
PH
Like
3404. Yeah. So the question is, what is your view on the potential of combining quantum computing with RL, which I believe is reinforcement learning? And continuing along that line, since I also work on data science and related problems, what, in your opinion, are the areas of machine learning which can impact or benefit highly from quantum algorithms? Because the kind of work that I've seen as of now is sort of limited to data dimensionality reduction kind of problems. What is your opinion on this general issue?
This is a very good question, a very open question, and a question that I don't think anyone in the community has an answer that fully agrees with each other. But I can share with you my opinion.
Yeah.
So in this scenario, well, I would say the interface between quantum computing and machine learning in general is really just beginning to be explored. It started off really about 2016 with AlphaGo sort of getting everyone interested in machine learning. And so there's a lot of different scatter techniques. And the first algorithms that started looking at how machine learning could benefit from quantum computing was taking some of the existing quantum algorithms and applying them into machine learning. And what I mean by that is, if you look at machine learning, there are a bunch of sub-protocols, subroutines, and then they go, this subroutine might be able to be accelerated using quantum computation. And namely speaking, one of the culprits there was Seth Lloyd and his LLH algorithm for inverting linear equations. And with that, with a lot of machine learning dealing with large matrices and large vectors, they were able to find ways of modifying LLH or variants of LLH that was beneficial to machine learning. And of course, Subsequently, there was sort of these cluster sampling and a few other one of these algorithms, and so they would, I would classify as one class of algorithms, and of course, these aren't really reinforcement learning algorithms per se. Most of them are just, a lot of them are basically you're given the data and they just supervise learning. But on the reinforcement learning side, less has been done. The only thing I'm aware of is some work by Hans Briegel. So he did these quantum agents, and he was looking at agent-based learning, where he made use of the Grover search algorithm to get a quadratic improvement in the search of strategies. We don't know if there are capabilities beyond that, but I wouldn't rule that out. So one of the areas that we're looking at certainly here in terms of this relation is that we're moving towards interfacing quantum computing with reinforcement learning. Because as you saw, we had these interactive agents. These agents and these agents are basically the fundamental building block of any reinforcement learning algorithm. In reinforcement learning, we have agents. These agents, they send out outputs, they receive stimuli, they get a reward for certain stimuli, and then they update themselves and so forth. And that's essentially your reinforcement learning algorithm in a nutshell. The question is, can such an agent, for example, explore many different outcomes at the same time? Would there be certain instances where it can sort of find a more efficient ways of updating itself quantum mechanically? Those things we really don't know. I speculate, and I'm very confident to say that in these cases, there should at least be a quadratic speedup, thanks to Grover search. For exponential speedups, they are a lot harder to find, and it would require a lot of thinking. But one potentiality does come from the dimensional reduction, because when you have far fewer dimensions, the number of gates you need is far less as well. So if there are families of strategic behavior where the dimensions of the quantum agent is exponentially smaller than the dimensions of the classical agent, I wouldn't be surprised if the number of gates required is exponentially reduced too. Of course, to formally prove something like this would be very challenging and would require perhaps some very deep thinking on the mathematical techniques. So no guarantees there. So that's on the machine learning side. In regards to your question on the other side, maybe I'll let you to ask the next question that you have in mind.
Yeah.
Great, thanks.
What does quantum computing mean for data integrity? Does it depend on the same factors as classical computing, or is it different?
I'm not quite sure what type of data integrity is being referred to at this point. If it is in terms of the integrity of the computation, in terms of error correction, then absolutely quantum computers require their own error correction protocols to be able to work in a scalable manner. Just like in classical computation, when our data when there are fluctuations in our data processing, and there are fluctuations, what we have is we have error correction protocols that, through redundancies, allow us to correct for errors. Similarly, quantum error correction algorithms exist as well, allowing us to be able to, in principle, correct for any quantum error given sufficient redundancies. In general, in practice, of course, it's a lot trickier, and the demonstration of full error correction is still something that is currently in experimental development. But the fundamental principles, I don't think, are that different. I don't know if Said meant a different notion of data integrity. So if he does, please just clarify, and I'm happy to answer any other notion of data integrity, if it's in terms of, say, information security or cryptography or so on.
Thank you, Prof. Another question that is more generic in the sense that it has come up among the discussions of people who are organizing this talk is that what are the most important problems, as in that you think, in your opinion, are to be maximally benefited by the quantum computing realm, if I may put it in that way, and what are the problems that won't be affected much?
That's a very good question. It's also, if I could answer that very confidently, I'll probably win a few prizes. So again, I can only speculate on this. So when we ask this question, I guess there are two things. There's one is near-term quantum computers without error correction, like what
Mm,
Google currently has, and
mm,
there are distant quantum computers with full error correction. And the types of problems that they can tackle will be drastically different. If we go for full universal quantum computation, then of course we have Shor's algorithm, which we know is able to factor numbers efficiently, and uh, and so that will of course have a lot of consequences for sort of the current way that we do information security.
yeah,
And
cryptography will eventually break if you have that kind of a realm, right?
absolutely.
Yeah,
And we, of course, we don't know what other MP problems quantum computers can solve. That remains an open question, which is also one of the areas that makes post-quantum cryptography a little risky in the sense that one might come up with a MP problem for post-QKD, but then someone comes up with a quantum algorithm to solve it.
right.
So with full universal quantum computers, I would say that our current understanding of their capabilities is fairly rudimentary. Because imagine people trying to program classical computers without classical computers. Most of the algorithms that we have today have come about with experimentation, with classical computers readily available, so that we can play around with them. The development of computer algorithms in the 1940s and 1950s was fairly rudimentary. Of course, we had a few key ones which people can come up with, but since everything is done semi by hand and we can't test them, we can't build very advanced algorithms. And I would say that quantum algorithms is in that sense in that same boat. Of course we are seeing a lot more interesting stuff like the inversion of linear equations by Seth Lloyd, which has a number of potential interesting applications. We've recently seen some very interesting sort of protocols for quantum algorithms for finding the distance between two sets or two regions of space, which is quite nice. You want to minimize the distance, and so there are a lot of potentially very interesting algorithms along those lines. In terms of the near-term algorithms, though, these things would all be impractical because they require very fine-tuned ability to error correct. Near-term is more along the lines of what they call quantum simulators and variational eigensolvers. So quantum simulators and quantum modelers are a little bit like what I demonstrated here in sort of my protocols, in that the goal isn't to solve a computational problem, but rather to simulate certain statistics. And in this scenario, while errors will still get in the way, at least you can have a certain amount of advantage in your simulation. And indeed, the most obvious thing quantum systems can simulate is quantum systems. So probably the first things that we will see quantum computers being used is in the era of quantum chemistry, where they used to simulate certain quantum interactions and allow us to sort of make predictions about certain chemical properties from the ground up. Um, Simulating other complex systems like I do is certainly possible, but it requires more legwork because if you're simulating a non-quantum system, you need a translation. And when you're simulating a quantum system, you know what the Hamiltonian is, and you just go and simulate it. The other area is in the so-called variational eigensolvers, which are basically based on the idea that because of entanglement, a quantum computer has different qualitative properties in exploring or sampling regions of probability distributions. That what I would say the intuition on why they work. The idea is that because quantum systems get correlated so quickly with relatively few quantum bits, you can start generating probability distributions that would otherwise take a lot more gates to generate classically. And because of that, one might be able to sort of use certain numerical optimization algorithms like variational quantum algorithms or VQOAs to be able to sort of search for certain solutions faster. But these things are quite blind in that there is no real proof that they are particularly advantage for any problem. And they are reminiscent to me of black box machine learning, where we try various techniques, like we take 3 layers and then we do a hotfix by taking the first layer and link to the fifth layer, and voila, it does better because somehow the correlations are passed in more quickly. Similarly, a variation of quantum eigensummons and so on operating a bit of a black box in that they seem to work well for certain problems, and we have some intuition on why they work, but there's no proof that they're going to be better than their classical counterparts in the most general, in any realistic, useful case. So that's roughly the region we're at and the region we're going. In terms of my personal intuition, I believe the real advantage of quantum computers is in their parallel processing and their randomness processing. They are able to process randomness a lot more effectively than classical computers. So I think one of the biggest places we will see them is in any algorithms that involve sampling. So for example, search algorithms, optimization algorithms often can be shortcutted through sampling. Machine learning algorithms can be sort of involve a high degree of sampling. When we can sample many things in superposition and find out properties about them, then these are the things that can be speed up by quantum computers. For highly non-parallel computation involving very deterministic sequences of data, that's where I least expect quantum computers to be useful.
Thank you. We have one last question from the audience, which is that when you mention a quantum approach to create new models and simulations to interpret or study systems, is it necessary to strictly apply the rules of quantum mechanics? Would it be an interesting approach to mostly take an inspiration from the principles of quantum mechanics to create some kind of pseudo quantum model to help with interpreting complex systems?
That's a very good question. So, so far we use quantum. So I guess it depends on the goal. So far, our purpose is that we want our models to be realizable in reality, in the sense that the model we build isn't just a mathematical model, but the memory advantages can, in principle, be realized by an actual computer or actual system. We can certainly use quantum-inspired models, but then it becomes more difficult to say, okay, first of all, are these quantum-inspired models realizable in reality? And if they are they just realizable by classical computers? And if they were realizable by classical computers, is the memory of the pseudo-quantum logic the same as the memory of the classical computer used to simulate the pseudo-quantum logic? So there are all these questions to be answered. What makes quantum mechanics quite useful is that, or quite fundamental, is that ultimately everything in the universe is quantum. If we have a two-level system, in principle, a superposition of those two-level configurations exists. In practice, often it's just very hard for us to access those systems. So we think about them as classical systems. So really, the world is ultimately quantum mechanical. So that's one motivation of using quantum systems, because it tells us fundamentally what is the minimum memory needed to simulate if we had full computational power at our disposal. That said, there is a class of theories known as generalized probability theories or post-quantum theories. And these are probability theories that go beyond quantum mechanics, that offer either higher degrees of non-realism or higher degrees of non-locality. And one can start asking, hypothetically, what happens if we were to build models out of these things? I haven't really explored in that direction because we don't know whether these models can ever be built, since they require exotic physics that we don't know whether they exist. But there are certainly people exploring such models in other instances, namely most often in areas about locality and stuff, where they want to understand what makes quantum mechanics special. So they think about theories beyond quantum mechanics, and they think about what axioms rule out all these more exotic theories, so we end up with quantum mechanics.
Right. Thank you. We have just a couple of more questions before we can.
Sure. No worries.
Yeah. So if you have time, then we'll go forward.
I'm most happy to answer all the questions.
Yeah. So since this is a session on discovery science, right, which is the overall topic of this series, the question that came to our mind is, what, in your opinion, would be the eureka moment in this quantum computing field, as in some particular event or a finding or an observation that has already happened, or is something that we are striving towards, which has or would in the future
Hmm.
change the direction or the way we understand this topic as a whole?
That's a very good question. So it's easier to answer the eureka moments that happened in the past than what will happen in the future. So I'll first address the things that happened in the past. To me, a eureka moment is, as you say, is something that fundamentally changes our way of thinking about things. And so, in that sense, I think the most of the eureka moments are when new theory gives us a new way of understanding or approaching problems. Looking back at the development of quantum information, quantum computing, there's a few moments that I could probably classify as being eureka moments. The first is the discovery of what's known as Bell inequalities or the non-locality equations. Well, what these were was that before them, we had people like Niels Bohr and Albert Einstein argue, is the universe local? Is the universe non-local? Is the universe realistic? Is the universe non-realistic? And it was considered a purely philosophical debate. Till a man named John Bell in the 1960s gave this mathematical equation that said that it doesn't matter what theory your universe is based. It could be quantum, it could be classical, it could be some exotic non-quantum theory. But as long as the universe is local and realistic, meaning that every object had everything you can measure about the object is stored inside it, then it had to satisfy a certain inequality. And this gave a way of experimentally verifying whether or not the universe was actually a local, realistic universe. And most of the people thought the world was locally realistic, even though the mathematics of quantum mechanics predicted that the inequality would be violated. So up till the 1980s, before the experiment, so John Bell proposed this inequality, and people was like, okay, quantum mechanics is gonna break. Quantum mechanics is gonna break. There's no way that we're going to see this sort of exotic entanglement in real life, because everyone had this belief that, as Albert Einstein said, we believe the moon is there even if we don't look at it. And a non-realistic universe would say that the moon may not be there if we don't look at it. So people were deeply troubled by that view. But nevertheless, Bell inequality said that we could test it, and when it was tested, Bell inequalities was violated by quantum systems, which led to the conclusion, the forced conclusion, which I would say was against about 80 to 90% of the scientists at that time, that the universe is actually not locally realistic. And that gave birth to the potential for quantum computing and quantum information. So I would say that is one of the eureka moments. The second eureka moment is probably Richard Feynman, who gave one of the first talks about quantum computers. I mean, it didn't have much actual mathematics in it, but he was the first person to say, wait, if quantum systems are so complicated, can't we use these complicated systems to understand other complicated systems? I mean, it wasn't like it was a new mathematics, but it was just a new way of thinking that people haven't really thought about before. Previously, people have always thought quantum systems are entangled, they're hard, they're measurement, we don't understand them, this makes them annoying. But Feynman's view turned it around to say that, hey, these things can actually be very beneficial. And I would say that in conjunction with this, Charlie Bennett's discovery of quantum cryptography and Shor's discovery of Shor's algorithm cemented these ideas. So I would say these things was the second, combined would be the second eureka moment that went from quantum information, quantum physics is something a challenge we have to overcome, to a resource that we could use for more advanced computation. And the final eureka moment that I would say happened was the discovery of quantum error correction. Because before the discovery of quantum error correction, most people thought that it was impossible to correct for errors in a quantum computer. And there's good rationale for thinking about this, because a qubit is a continuous system, right? It varies continuously in space. So a lot of people got the intuition from classical analog computers, which was these, capacitor resistor computers that people used back in the 1950s and 1960s. They were great for solving differential equations, but they were terrible for scaling because they can't error correct themselves. And people thought that quantum computers, with qubits being continuous parameters, would never be able to error correct. But it turns out that they had enough discreteness from the discrete measurement outcomes for error correction to be realized. And they discovered the first error correction algorithms, which gave a threshold to say, if we reach these fidelities in quantum gates, we can build a scalable quantum computer. That was the final eureka moment, I think, that suddenly made people say that all these pipe dreams that Feynman had could actually be made real. So I would say that these are probably the three biggest eureka moments in terms of quantum information that happened in the past. In the future, it is much harder to say because by virtue of what I think about as a eureka moment, it's something that fundamentally changes our theoretical perspective or theoretical understanding of things. So naturally, a eureka moment should be something that we don't expect. So eureka moments, moments of eureka, I think, are precisely the ones, the deliverables that we can never put down on our grant because we don't expect them to happen. So they will never be funded, and they will always be discovered by accident, kind of like penicillin.
Right.
But for example, I mean, if I was to go for very rough speculations, wishful thinking, maybe.
Yeah.
If someone could someone could make a concrete proof of quantum computers being able to say solve NP-complete problems, that would be, of course, extremely major. Currently, we know that we believe quantum computers can solve several NP problems, like factoring, but we don't see a way of solving an NP-complete problem. If we could solve an NP-complete problem, then it means that every NP problem can be solved by a quantum computer. Most people don't believe this is the case. Okay. But if someone was to find a technique to do that, that I would certainly classify as a eureka moment, because that would basically get rid of pretty much all of our current post-quantum stuff. It will get rid of one-way functions, right. And that would it would challenge these ideas of whether P equals NP makes sense as a question in the quantum regime. Of course, we also have quantum P versus NP, which is a QMA versus BQP. But it would say that, look, at least from the classical scenario, there is no longer this irreversibility in problem solving. And that would, of course, be very exciting. Right. But again, that's unexpected, which is why it would be a eureka moment. I would never write a grant to say I will solve this, and I would never fund the grant probably to say I will solve this, because unless they give me a very convincing technique, which means they already solved it. So yeah, so this is the nature, which is why I think it's very useful to. We have a lot of grant-driven research where we have concrete deliverables, but it's very useful to have a mix of blue skies, flexible funds for people to actually tackle these eureka projects. Very high risk, 10% success rate, but immensely useful if they succeed. Kind of like venture capitalists funding startups.
Right. One final question before we wrap up, and this has come from a PhD student at SUTD, which is, what is one key takeaway on your research and findings for future research scientists looking at quantum simplicity?
So what are the key take-home messages in this case? I guess the take-home messages here is that complexity itself, which has always been considered to be an extremely fundamental concept in complexity science, is ultimately dependent on what sort of information processing we use, or what sort of information we use, whether it is classical or quantum mechanical. And that ultimately our perceptions of what is complex in our reality is basically a limitation of our capacity to process information classically rather than quantum mechanically. That if we had an organism that was capable of processing information quantum mechanically, they may have very different views of what in the world is complex, what problems are hard to solve, and what is simple. And it's always interesting to keep this in mind as we are going into the domain where quantum information processing is becoming a reality. And it's very likely that there will be fundamental paradigm shifts on what we think is solvable and what we think is non-solvable from a practical perspective.
So I think we do not have any further questions from the audience or myself
I think you
included.
had one last question about the recent controversy between the classical and the quantum, right? With the classical simulation, and you sent it to me by email.
Oh yeah, so yeah, exactly. So that was more about this. So there was this work by MIT in 2013-14, which said that you can have quantum speed up on dimensional reduction problems, and that in that area. But then recently there was another paper from I think University of Washington, which strongly contradicted that
Ah,
claim.
yeah. So it's a very interesting. I prompt you to ask that question because I actually did some homework on that one. Since it's the most technical one, so I actually
Yeah.
had to really look it up and have a chat with actually Patrick Robintroft, who is actually in Singapore, by the way, one of the top quantum algorithms people. So
Okay.
it's quite nice. So what happened in this is that as mentioned in 2013, Tesloid and stuff came up with some very interesting ideas for potential exponential speedup. Most of it are based on these ideas of inverting exponentially large matrix. Now, in principle, the HHL algorithm could invert a sparse matrix efficiently. So sparse matrix is basically one where it's mostly zeros, but there are a bunch of there's a bunch of non-zero terms, but the bunch of non-zero terms should be a very small fraction of the total number of zero terms. And with those things, they can invert them efficiently on a quantum computer, but they can't be efficiently inverted on a classical computer. Now, as a subset of those sparse matrices, matrices with very small rank. So these are matrices, low rank matrices. Now, so with these low rank matrices, they came up with some other algorithms, like say the recommendation systems, and and sort of this cluster detection, cluster sampling protocols, and it turned out that a very brilliant student by the name of Irvin Tang, who was actually an undergraduate at the time, was decided to look at these algorithms, and and this was completely unexpected that she found that the recommendation system algorithm that people thought would had a quantum speed up, there was actually an efficient classical algorithm for. If she followed the quantum logic and they used the quantum sampling processes and tried to mimic the quantum process as much as possible, she could she could build a classical algorithm that was up to a polynomial as efficient as a quantum. I should say up to a polynomial because it's a pretty bad polynomial. It's
Yeah.
like to the 16 or something.
Okay.
But it was a polynomial. And and I think that's a very nice illustration that we just really don't know enough. That certain algorithms that we think, okay, we have a full quantum advantage, but it turns out that classically it is still simulatable. And so one of my research areas is in quantum resource theories, which is to understand the fundamentals of what quantum processes are simulatable and which are not, to help sort of isolate these cases. But going back to this question again. So what happened was Irvin did this, and then she realized that her classical algorithm could work for any bounded rank matrix inversion. So a lot of the quantum protocols that was based on inverting a matrix of small rank, we now know a classical algorithm to do. But for inverting general sparse matrices, there's still an exponential speedup. And I should say that there's another assumption in Irwin's work that is likely to be quite impractical, which is that she makes this, what she calls a sampling assumption, which is that she assumes that there's some database out there that is exponentially large that stores the large complex vector. So there is a very large complex vector out there that can be stored in quantum memory, in classical memory, that can then be accessed in a very efficient manner, despite the fact that there is an exponentially large database. This assumption naturally requires exponential memory. So there is an exponential memory built in there somewhere, whereas that doesn't necessarily have to be true in the quantum case. Because in quantum case, that quantum memory can be stored in a linear number of qubits. And this is why those results are still controversial.
Right.
But if you make the assumption that there is a very efficient, exponentially large classical database that can be accessed in sub-exponential time very quickly, then you can get this polynomial, then you can get these nice classical algorithms. I'm not saying that these are uninteresting results, they're very interesting results, but their practicality, the classical algorithms, in my opinion, still yet to be seen. And which is why there's still a lot of debate going on.
Right. Right. Which is why, like, when I was doing a little bit of research in this area, I came up across this kind of discussion
Contradicting
on,
views, yes,
yeah,
yes.
contradicting views, and therefore, like, that drew a lot of attention among a lot of researchers. uh,
Absolutely.
yeah.
But I think this line of research is very important because we want to pinpoint where quantum advantages lie. We know for sure, well, we don't know 100% for sure, but almost for sure that quantum algorithms have advantage because what happens is that if they don't, then you get this collapse of what the computer scientists call the collapse of the polynomial hierarchy, which to
Right.
them is very, very bad because it means that pretty much all these different classes of problems which they thought was much more difficult all
Mm.
have the same difficulty. So almost everyone believes that quantum computers have a computational advantage, but we just don't know which ones they have advantage
Mm.
and which ones they don't. And sometimes, even when they don't have exponential advantage, it's still quite cool that they can help us inspire new classical algorithms by thinking about them in a quantum manner. And Irwin was only able to come up with these answers by trying to mimic a quantum computer. So perhaps that would be one way we can think about efficient classical algorithms in the future. What's the best way of simulating a quantum computer when we don't have one?
Right. Right. So I think then that should round up our wonderful discussion this morning that we've had on. Firstly, thank you, Prof, for the talk, and then entertaining all our questions from the
Thank
audience and myself included. Thank you for taking out the time and you know enlightening us on a topic that's very interesting and that will gain relevance more and more as we go into the future.
Thanks.
So,
I guess I'd like one final word, which is to those of the audience who are in data science or computer science, that you
right,
shouldn't be intimidated about quantum information, quantum computing at all. That it's a subject that does not actually require that much physics to get into. And some of the very top people in the field came purely from computer science backgrounds. So if you're interested in this topic, and you haven't taken a single thing, a course in quantum computing, quantum information, it's not too late. I mean, reading reading up on the very basics of quantum information to get into it. It's not much harder than sort of reading any other thing about sort of applying your data science algorithms to say quantitative finance. So if you're interested in these areas, don't be intimidated and don't be scared. Look out for the opportunities because if you're interested, the opportunities are out there. Thanks.
yeah. So,
Cool.
yeah. I would also like to take this opportunity to thank all the participants, everybody who joined us this morning, for listening into the talk and also coming up with questions so that we had a very nice and fruitful discussion. What I'll do now is for the participants, I'll put up a screen for a QR code to scan so that you can give us some feedback. And that would be lovely for us to improve on our webinars going into the future. And thanking you, Prof, one last time. Thanks.
Thank you very much and have a great day, everyone.
Yeah.
Bye-bye. Take care.
Bye.